question about would be the Vaillant Dam one, so that's one that we had quite a lot of detail. But when I'm marking that, I'm not going to be looking for what year did it happen or what was the volume of that particular landslide, right? I'm not really interested in that. What I'm interested in was what were the things about that that could be applied to other places. So the question would be something like, what were the risk factors there? And you could say things like the fact that the strata were dipping towards the reservoir with the slope, or that there were weak clay layers within the strata. So do you see what I mean? So I'm rather looking for the principles than like facts about that particular one that couldn't be applied elsewhere. So what should have happened, so last week in the Monday and Friday sessions both did a practical on landslides, but you haven't been given them back yet. So what I was intending to do was to basically, because you can't revise something that you don't have, and I could have given the Monday group theirs back yesterday, but I couldn't really have been confident of getting all of the Fridays back to everyone in that group. So examinable for the exam, but because you haven't got it back, you can't revise for it. Having said that, a lot of the information which was in the practical were also in the lectures, right? So things like the Coulomb failure criteria that you used a lot in the prac, you could be asked questions about because that was in the lectures. Okay, so you've obviously been given lecturer evaluation forms as well as the lecture notes today. So just to be clear, that's just for me. So Trish should have already given you forms that cover her previously. So in this, and yeah, please do fill them in because they are useful. So for instance, the reason that you guys are getting the lecture recordings is because that was the single most common suggestion last year. So we do listen to them and try and take them into account. Yep.
That's the Trish's lecture as well.
So the way that it works is that in order to be recorded, the lecturer has to agree. So there's no like, you can't compel lecturers to do lecturer evaluations. And this is the first time that Trish has done the course, and she just said that she wasn't willing to do that, or she didn't want to do that. So that's why, so this, you know, for me and for Robin as well, Robin's already agreed. I mentioned that we're going to have the guest lecture in the email that went around this morning, so that's next Tuesday. Next Tuesday, again, that lecturer said that she didn't want to be recorded, so that's why that one isn't going to be recorded. So we're going to talk about earthquake hazard today, and when we're trying to work out where there is a risk of earthquakes happening, where there's a risk of death and damage due to earthquakes, there are two things that we need to consider. So one thing we need to consider are where are the places which are likely to undergo strong ground shaking in earthquakes? Okay, so that's one thing. And then also, what is the distribution of vulnerability? Okay, so if you have an earthquake which happens at the mid-ocean ridge in the middle of the ocean, that is not going to cause structural damage to building. It's not going to kill people. So one way you can think about this is you can talk about risk, where risk is equal to hazard times exposure. So there are two parts. The hazard is the geology, basically. So that's where are there likely to be earthquakes, how often are those earthquakes likely to occur, and how large are those earthquakes likely to be. And then you have exposure, and so that includes basically where are the populations. So is the fault near a population center? But it also includes architecture. So what are the buildings in that area? How well are they likely to stand up against earthquakes, and we'll talk a little bit about both of those. So you can think of this to some extent as being the geological side or the physical side, and this as being slightly more the human side, which involves engineering as well as other factors. So there are various ways that you can try and quantify the hazard, and so we're going to talk about that right now. The exposure is, I would say, difficult to quantify exactly, but you can make some attempts to do so. And we'll talk a bit about that. Okay, so how do we know where we are likely to find hazards? So how do we know which locations in places which are likely to have earthquakes? So one way that we can do, that we talked about in the last lecture, is we can look at how the Earth is deforming. Okay, so remember, we had these two models, one of which is plate tectonics, where you have a rigid shell, and all the deformation takes place at the boundaries around the edge. And we said that that was roughly what we saw in the oceans. For people that haven't done the practical, we talk about this again in the practical, but you don't need anything from that to understand this. And then in other places, mainly in the continents, we actually get deformation spread over a very wide region. So these are GPS vectors. They're showing the northward movement, which is driven by India moving northwards. And you can see that that compression is being taken all the way from the Himalayan frontier up to Russia, up to Siberia in the north. And so there are thousands of kilometers of broadly distributed deformation. So one thing that you can look at to work out how great the hazard in a particular place is you can look at the GPS vectors. You can see how much strain is being taken up in a particular place. And if you have larger amounts of strain, that means you're going to have more frequent large earthquakes. So this is sometimes called, or this type of information is sometimes called geodesy, which is basically just a fancy way of saying that you're measuring the Earth. Okay, so that question was, which is a good question, isn't it the case that earthquakes can't be predicted, so what's the point? So the answer to that is, you cannot say that tomorrow there is going to be an earthquake here. Okay, that is not possible. You can't predict in the short term. You can't like ring an alarm and get people to leave the building before the earthquake happens. What you can say is that this area, due to the amount of strain that you can see in the GPS, is accumulating enough strain for there to be a magnitude 8 earthquake every 100 years. And if you look at the historical record in a particular place, you will see that like a particular fault will be loaded for some number of years, let's say 100 years, and then there'll be an earthquake, and then it'll be loaded again, and then there'll be an earthquake. And not everywhere is like that. So in many places, the return time for a large earthquake will be extremely large. It may never happen in the underforming interior of the plates. Okay? Whereas in other places, you can say that you don't know that it's going to happen tomorrow, but you know that in the next 100 years or so, there is going to be an earthquake in that place. And so if you then need to build that into your building codes. Okay? So you know if this is somewhere that is going to have an earthquake every 50 years, say, you need to build your buildings to withstand the earthquake, which will happen at some point in the next 50 years. Even though you don't know when exactly it is, you can still use the hazard, the likelihood. The way that we measure hazard, we'll come onto this later in the lecture, but basically the way that we measure hazard is how likely is there to be a particular amount of ground shaking, a particular amount of ground acceleration in a particular period of time. Okay? Does that answer your question? It is a good question, though. It's good to think about what is the point? What can we say? So another way, so we've said geodesy, we've said looking at the amount of strain accumulation in GPS. Another guide that we can use is where there have been earthquakes before. Okay, so this is a picture of Central Asia. The red dots are earthquakes. You can see that there are some areas which have lots of earthquakes, and some areas, such as India, where there are relatively few. So the past is going to be a guide to the future, and so you can say that it's likely that where there have been large earthquakes in the past, you're more likely to have them in the future, and so you would say the hazard there was greater. Another thing that you can do is to actually see the signature of these active faults in the landscape. So where you have brittle movements on a fault, that actually is going to, so if you have a thrust fault, for instance, so remember a thrust fault was one in which the hanging wall moves up like this. After you have an earthquake, you're going to have created a topographic step in the landscape, and so you can also use satellite imagery and field work to identify active faults in the landscape, and large earthquakes generally occur on pre-existing faults, not necessarily always, and so that's another guide to where you're more likely to have events in the future than in other areas. So there is a caveat to this, so there's a problem with this. You do get slowly deforming areas in the middle of the continents, and you can say South Africa, you can take South Africa as an example of this, where the repeat time for earthquakes, the amount of time it takes for the strain to accumulate and then be released in an earthquake, is many thousands of years, okay? So we do get earthquakes in South Africa, we'll talk about that later in the lecture, but we don't generally have faults which are moving rapidly enough that we could measure them with GPS, and we won't necessarily have seen earthquakes in the areas where future earthquakes can happen, because we only have about 40 or 50 years where we've had good instrumentation, and so we've been able to locate all the earthquakes that have happened. And if your repeat time is over thousands of years, you might just not have seen it yet. I will talk about where we have earthquakes later. Sure. So yes, so that's a really good example. So the Botswana earthquake, I can actually tell you stuff about this that nobody else knows because we're working on it at the moment. So the Botswana earthquake is not on what you would call the East African Rift. I mean, it's in an area where there have not been any recorded earthquakes in the last 40 years. So it's kind of, you can think of it as being in the middle of nowhere, okay? If you actually look a bit more closely, so if you look at magnetic data, which has been flown over the area. I don't know if Trish talked to you about mag data. Probably not, because it's not so relevant for most engineering applications. But it lets you basically look through the sand of the Kalahari, and you can see that there is a major fault there, which is very, very ancient. So it's a Precambrian fault. So we're talking about billions of years ago. So basically, it's a pre-existing weakness, which is being reactivated in that earthquake. And that earthquake is a really good example of an earthquake where there was basically no way that you would have expected an earthquake to happen in that particular place. So you do get these very occasional earthquakes within areas which are very slowly deforming. And so one example, so this is a hazard map in North America. We actually showed a more up-to-date version earlier in the course, but for this one, you see there's a very large red area which is in the center of eastern US. So that red area is the New Madrid region. So the New Madrid earthquakes happened in 1811 to 1812, and there were 3 large earthquakes, so magnitudes 7.5 to 8. That's a big earthquake, causes a serious amount of damage. And basically the only reason that that area there is red is because those earthquakes took place back in the 1800s. But that doesn't mean that you couldn't have a large earthquake here. I mean, before these earthquakes took place, you probably would have made that very low risk as well. So just to kind of make you aware of some of the disadvantages of these kind of maps, there's a statistical, I guess, problem or a statistical fallacy, which is called Texas sharpshooting, where the idea is you have some randomly oriented points, and then after you've had them, you then draw a ring around them, and then you say that that is the area which is high risk. But actually, it could have easily been over there, right? It's just that these happen to be the small number of points that you had when you were making this hazard map. So you can make these maps. They are useful. There are also problems with them. So the point of
So in 50 years, we are saying
is a dangerous assumption to make. So this is going into, so the question there was, if you've got an area which had an earthquake, is that area then safe? Okay, so the energy has been released, so it's now safe. I mean, it's a reasonable question. It completely is a reasonable question. The reason why it's a dangerous assumption to make is, let's say you have a fault. So this is my fault plane, and then part of it fails in an earthquake. So this is an earthquake. This part of the fault plane ruptures. This particular patch is going to take time before the elastic strain can reaccumulate so that it can cause another earthquake. But actually, this area immediately next to it, immediately along strike, will actually have been loaded by this earthquake. So actually brought closer to failure. Do you see what I mean? So the specific patch that fails should take time to build up the strain again, the elastic strain, to generate a new earthquake. But it's not a good idea to say, oh, we've had a big earthquake here, therefore we aren't going to have one in the future or in the immediate future, because actually the very next section of the fault along strike is actually probably more likely to go immediately after this earthquake than it was previously. Does that make sense? So there is this stress transfer between earthquakes, between sections of the fault. And actually, if you go to somewhere like Turkey, if you look at there's a fault that runs a length of Turkey in the north, and over the last century, first there was an earthquake here, and then the next segment failed, and then the next segment failed, and then the next segment failed, with about between about 1 and 5 years in between each earthquake. And Istanbul is here, basically. So in Istanbul, this is something that this stress transfer between segments of faults is something that they worry about a lot. Because the idea is that this earthquake will have loaded the section of the fault with underneath Istanbul, and so probably you would say it's more likely that it's going to happen in the near future than it was previously. And that fault, if you look at the historical records, you can see a number of times in the past where you've had this cascade of earthquakes along the length of the fault. Okay, back to this slide. The point of this slide, the thing that I wanted you to take away from this slide is one thing that a lot of people say is, I don't live on a plate boundary, plate tectonics, all the deformation happens at the boundaries, therefore I don't need to worry. So basically this is showing you a graph of fatalities in earthquakes over the last century, and the blue bars are showing you earthquakes which happen on those plate boundary faults, and the pink bars are the values of fatalities caused by earthquakes within the continental interiors. Okay, so blue plate boundary, pink within the continental interiors. These numbers are the number of earthquakes which contribute to this bar. So basically what you can see is that while the largest earthquakes tend to happen on the plate boundaries, they don't actually kill cumulatively as many people as large numbers of earthquakes, which are smaller, but are happening within these wide, broadly deforming regions. And part of the reason for that is because on those plate boundaries, people know about the earthquake risk. Whereas in the continental regions, the interiors, which are typically much more slowly deforming, the building codes are generally much less good because the risk, or rather the hazard, isn't as well known. So the exposure is greater because the building codes aren't as good.
Interior ones happen a lot more.
So this is because we're only looking at earthquakes which have caused a lot of damage, which have killed a lot of people. So the largest earthquakes, so certainly above 8, you get far more on plate boundaries, but actually many of those events do not cause significant loss of life, and so wouldn't be included on the diagram. But you do also get, I would say, yeah, I think it's true to say, you get more of these smaller earthquakes within the interiors than the very large ones that you get on the boundaries. Part of it is a lot of the plate boundaries are going to be beneath the sea. So all of the mid-ocean ridges, for instance, you're going to get a lot of earthquakes there, but it's not going to make it onto this diagram. Again, another thing that I just want to point out is that if you look at the last century, this is fatalities of earthquakes over the last century. And you can see that there hasn't been, and this is amount of earthquakes, this is amount of deaths relative to the global population. So basically the population is going to increase, and so you'd expect the number of fatalities to increase because there are more people exposed to the same hazard. But even taking that into account, there hasn't really been a decrease in the rate of deaths due to earthquakes, which you might expect, right? If you think about the progress which has been made in engineering and in architecture within the last century, you might well expect that the number of deaths would be going down. And that isn't the case. And actually, this red line here is specifically looking at deaths which were caused by building collapse due to shaking. So that is the thing that you really would be expecting to be reduced by better engineering, and you can see that that seems to have even gone up over the last couple of decades. And the reason for this is basically not just the number of people, but where people live. So the last few decades have shown increasing urbanization. So basically you're moving people from the countryside, often in quite small structures which are made of materials which are less heavy, which are less likely to cause crushing injuries during a building collapse, into often poorly made large buildings within the cities. Okay? And so you have an earthquake which hits a city. Now it's going to cause a lot more casualties than it would have in the past. And we're going to talk a little bit more about this in a second. So one of the things which correlates surprisingly well with the number of fatalities in earthquake is the corruption perception index. So this is something which is done by an organization called Transparency International. It's basically just done as like a questionnaire where how corrupt people perceive things to be in their country. So it's not perhaps the most scientific measure, but with these kind of things, it's very hard to get accurate measures, because how do you measure how much corruption there is? Now, there is a tendency that so basically a higher score means is perceived to be less corruption, a lower score means it's perceived to be more corruption, and there's a loose trend with gross national income per capita. So generally the countries with the higher gross national income per capita score better in terms of corruption. But if we look at the number of earthquake deaths, so basically what this is trying to show is as you go up, you get more earthquake fatalities, okay? As you move along this axis, this is your transparency index. So basically things which are plotting over here, places like New Zealand and Chile, they have very low corruption, okay? And then this axis here is basically showing how bad the corruption is relative to what you would expect from the gross national product per capita. So basically, if you're plotting in this section here, in this section, it means you are perceived as being relatively corrupt, but you're also more corrupt than you would predict just from the amount of money that the country has, okay? So you've got, the reason for doing this is, what you can see is the places which have large numbers of earthquakes are all plotting, or almost all plotting, within this rear quadrant. So that means that as you have poorer countries, those countries will typically have more deaths due to earthquakes, which is partly because you tend to have less money being put into building earthquake-proof buildings, because obviously that's very expensive. It's to some extent, you could think of it as a luxury for a country which was very poor to begin with. But even when you account for that, if you have a country which is relatively poor but is doing quite well in terms of corruption, you have relatively few earthquake deaths. Whereas if you have one which is more corrupt than you would expect just from the amount of money they have, that's where the earthquake deaths are really bad. And you can see that of these, really the vast majority of them are plotting in this lower quadrant. And the reason for this, if you're talking about corruption, basically the place where you have, one of the places where corruption is generally most rife is in the construction industry. Okay, so globally speaking, the construction industry is one of the places where corruption has a very big effect. And one of the main aspects that corruption takes is not building to code. Okay, so a lot of these places, so Iran falls within this quadrant, relatively corrupt for its GDP, and it has really good building codes. Basically what they did in Iran was they pretty much looked at the Californian building code and adopted it. Unfortunately, nobody follows the building codes in Iran. So I've been to Tehran, like I've done fieldwork there, I've been looking at active faults within Tehran, and on the fault, within alluvial material, we'll talk about why it's the fact is alluvial material is bad later in the lecture, but you see department buildings being built without really any foundations, or with very shallow foundations. And I've been there with people from the Geological Survey, and they've gone to the contractors and been like, you know, this isn't to code, you have to dig down to bedrock, and the answer that they get is just, it is bedrock, when it isn't, it clearly isn't. Like, it just is basically unconsolidated sediment, but those large building companies in Iran are politically connected, so there's nothing that the Geological Survey can actually do to enforce it. And it's not just corruption, so it is also other types of architecture as well. So I think I mentioned this in a previous lecture, but within Iran you have a lot of these adobe mud brick houses, and they're particularly bad in earthquakes, because rather than the buildings collapsing and leaving voids, as you generally get with concrete buildings, when you have adobe buildings, it basically just turns into a thick layer of dust. So there's no voids, so people suffocate before that they can be dug out. So in 2003, on Boxing Day, there was a large earthquake which hit a town called Bam in eastern Iran, and it was about 30% of the population of the town were killed in that earthquake. And that's basically directly because of the building construction. So in the same way, a larger earthquake somewhere like Chile or Japan would have maybe 0.01% casualty rates. Okay, so in terms of how much damage an earthquake's going to cause, it's really about how much ground shaking that you have. And this is one of the older ways of measuring the size of earthquakes, basically through descriptions of what people have how people have described the earthquake. And one of the reasons I put this in is because it's quite an interesting document. So it is something which is used scientifically, but I'd just like to point out a couple of the features that they're looking for. So for an intensity 5, so this is a shaking level of 5, felt by nearly everyone, many awakened, some dishes, windows broken, unstable objects overturned, pendulum clocks may stop. And then as you go further down, so if you're going to something like a 10, then you have some well-built wooden structures destroyed, most masonry and frame structures destroyed with foundations. So notice wooden structures are actually doing better than masonry and frame structures. Rails bent. And then by the time you get to 12, you have damage total. Lines of sight and level are distorted. Objects thrown into the air. So what that means is that the acceleration of the ground is actually greater than g. So rather than just being shaken, everything's literally thrown into the air. So if you imagine a building is thrown into the air and then lands, by the time you're getting up to those types of levels, it's extremely difficult to produce earthquake-proof construction. This is also a side issue. The exact table that you use here is also quite culturally specific. So this is the one which is probably most commonly used. If you go to Japan, they have their own version, which has things like outdoor vending machines falling over as one of the criteria, because apparently outdoor vending machines are very common in Japanese cities. But this isn't such a good way of measuring the actual size of an earthquake, because it depends on the amount of shaking you get at the surface, and therefore the damage to the structures depends on a series of factors as well as just the size of the earthquake. So one of those is going to be the depth that the earthquake happens. One of them is the attenuation. So by attenuation, I mean that as a seismic wave travels through the Earth, with each cycle of the wave, as you travel one wavelength further off, you're going to lose a small amount of energy, okay? And the rate of that attenuation is different in different places. So in eastern US and actually in South Africa, because of the geology, the attenuation is very low, and so an earthquake will be felt over much wider distances. That's one of the reasons that the recent Botswana earthquake was felt throughout South Africa. So the Richter scale, I'll talk about that in a second, okay, if that's okay. It's like the next slide, pretty much.
So, like
Okay, so the way that we actually measure the size of an earthquake, if what we're interested in is the earthquake rather than the shaking, is something that we call the moment magnitude scale. So that's this MW. You don't need to, I'm not going to expect you to reproduce this equation, okay? So you don't need to learn it. Basically what this is saying is that this is basically the amount of energy that gets released in an earthquake. So mu is a measure of the rigidity. W and L are just the width and the length of the patch that ruptured, so the area that moved. And S is the amount that it slips. And that's going to give you a very large number, okay, so times 10 to the 17 or so, depending on the size of the earthquake, obviously. And so what we then do is we just apply this correction to it. So we basically take the log 10 of that number, multiply it by 2/3, and then subtract 6. And that gives us our moment magnitude, which is a number which is basically between around 0 and around 9.5 for the very largest earthquakes, so the largest that have ever been recorded. And that correction is done to make the answer match what previously was called the Richter scale, which was basically a measurement of the size of the waves on a particular type of seismometer. But again, there were problems with that relating to the amount of shaking that you get, both the response of the instrument, but then also things like attenuation and the depth of the event. So now we use this equation, which is looking at the amount of energy which is released by the earthquake. So that's a more scientific way of measuring them, but it's connected to the Richter scale. If you hear them talking about the Richter scale in the news, they're not actually. They're talking about the moment magnitude scale, but they just haven't adjusted to the change in the science which happened about 30 or 40 years ago. And just to give you an idea, so each unit of magnitude, because of that 3/2 log 10, each unit of magnitude corresponds to a 32 times increase in energy. So a magnitude 7 earthquake is 32 times larger than a magnitude 6 earthquake. And this is just to give you some idea of the amount of energy which is being released in an earthquake. So if you're talking about the very largest earthquake, so a magnitude 9, then that is getting up towards, 15 times 10 to the 12 kilograms of TNT. That's the amount of energy which is being released. So maybe for reference, the Hiroshima atomic bomb, was around a magnitude 6 earthquake in terms of the amount of energy which was being released.
how far did the largest earthquakes usually travel?
How far, what the length is. So really quite far. So the largest ones, the very largest ones, can be hundreds of kilometers of a subduction. So normally they happen at subduction zones, and it will be hundreds of the kilometers of the subduction zone that it ruptures along. So what you typically find is after the main earthquake, you do very commonly then trigger earthquakes at either side on the same subduction boundary. Okay. So one thing that I'd also like you to know is that in terms of actual damage due to earthquakes, it's not just the ground shaking itself, it's also secondary hazards. So we've spoken about landslides before. I hope it's intuitively clear that if you shake an unstable slope, then it's quite likely to cause a landslide. There are also tsunamis, so we talked about that in a previous lecture. So that's when you have an earthquake which displaces the surface of the ocean, so it displaces the whole water column. And so then that'll travel as a wave over very long distances. And this is often the thing that does cause large amounts of damage at those subduction zone plate boundary earthquakes. Fire as well, so there have been some historical incidents where you have very large numbers of deaths due to fire. Think in a modern city what's going to happen to if you are in a city which has gas mains, so pipes of gas traveling through the city, those will tend to be ruptured during the earthquake, and so you have the potential for explosions and fires to happen from then. Yeah. Liquefaction, we're going to talk about that in a second. So liquefaction is basically if you have, as you sometimes do, if you have impermeable layers of sediment, and then you have a porous layer within those. So imagine a layer of sand with lots of water in the pores in between clays which are very dense, and there isn't really any pore space, the water can't flow through it. In an earthquake, what can happen is that because the earthquake disrupts the clay layers, the water can then flow up through the clay out to the surface, and effectively this moves everything down, so it basically allows this upper layer to collapse in as the pore fluid pressure, as this fluid gets squeezed out of this layer. So you're reducing the volume of that sandy layer with the water in because you're squeezing the water out. You're allowing it to move up to the surface, and this typically, well, it can do things like this. Okay, so one of the reasons that you do often find areas which have extremely large damage is where you have this impermeable layers with a water-filled sandy layer in between. That water then escapes through crevices which are created by the earthquake, and the whole thing collapses in. So this is actually another thing that you can do in terms of measuring the hazard. So we've talked about large scale, where are there likely to be earthquakes? So another thing that you can do is what's called microzonation. So you can look within your city, are there any particular areas where you have the correct conditions for liquefaction already present, okay? And in those areas you would say that there is a greater hazard. So even if they're exposed to the same amount of shaking due to the earthquake, the damage can be much greater. You can also get amplification of shaking, so basically resonance, where the depth of the sediment layer is similar to the wavelength of the waves of the earthquake as well. So you also get that amplification as well. So by mapping out the depth of the unconsolidated sediment and looking for evidence that liquefaction could occur, you can create maps of your city which locates particular areas which are more at risk. So we've spoken about the fact that landslides and rock avalanches can be triggered by earthquakes. So this was just to show you an example of that. But I want to go through that just to say that these events do happen in South Africa. Okay, so there have been 3 events which have been reasonably large, so over a magnitude 6, which have happened in the last century. So they don't happen very often, but they do happen. So Koffiefontein, that's in the Free State. You've had one which happened in 1932 off the coast of KZN, and in our local area, the Torbach earthquake. So that's a town and a valley about an hour and a half's drive from Cape Town. And in 1969, there was a magnitude 6.3 earthquake and caused a lot of landslides, so secondary hazards within the mountains, as well as brush fires. So even here, you do see these secondary hazards happening. And it did cause some casualties. So 12 people killed and $12 million worth of damage. So that would be, think about the amount of, even if you have a relatively small earthquake, so magnitude 6 is not a particularly large earthquake, the amount of damage it causes to buildings and the cost of that damage can still be very significant. And so these are some of the photos from then. So you see it derailed a train as well. You can see this photo, the photo on the far side for me, that's showing an actual fault rupture. So the fault at the surface. It doesn't look particularly impressive because it wasn't a particularly big earthquake. The earthquake didn't move that far. So the point that I wanted to make here is just say that we said that the amount of shaking that you have, so these are basically maps of shaking. So the red colors are basically showing you the intensity of the shaking. So you can think of these as mapping onto that intensity scale we talked about earlier. So the red areas are the areas with extremely strong shaking. And these two earthquakes, one from Central Asia, one from Romania, these are earthquakes which are the same size, but you can see this one, there were no red colors in the center. So there was no really, really strong shaking. And actually, the yellow colors extend even greater different distances. So the scales are the same on these two diagrams as well. And basically, the difference here was that this earthquake occurred deeper than this one. So this one occurred at the surface. This one occurred at 60 kilometers depth. This is in an area which very typically has earthquakes at that depth, but very rarely at the surface. And you can see that the pattern of shaking is very different. Okay. So if we think about what the strength of the shaking depends on, so obviously the size of the earthquake, the larger the earthquake, the stronger the shaking is going to be. The depth is also important, so deeper earthquakes are felt over a wider area, but the shaking is less intense. This actually applies to that Botswana earthquake as well. So in southern Africa, you do often find earthquakes which are somewhat deeper than you do in other areas. That earthquake was at about 25, 26 kilometers. And so that's another reason that it was felt not only in Botswana, but across southern Africa. So local side effects, so that's the amplification. If you have unconsolidated sediment with the right thickness to resonate with the waves as they travel through the earth. And then attenuation, so that's basically, as I said before, it's the amount of energy you use with each wavelength that you go away from the center of the source. Okay, so these are just some of the things which I'd like you to think about when you're doing the revision, as we've done before. And I think that we're going to stop there. So I put in the example in Alaska, but that was just if we had time at the end. And I would rather stop slightly early than rush through that. Okay, does anyone have any questions? We do have a couple of minutes, so does anyone have any questions about this lecture? No? Okay. So one other thing. So a couple of people have said that they would like a chance to ask questions before the test. So what I think I'm going to do is tomorrow, I'm teaching another course, so I have reasonably limited amount of time, but tomorrow morning, so after 10 o'clock, so basically from 10 o'clock to 12 o'clock, I'll be in my room, which is room 301 in the Geological Sciences building. And if people want to come and ask questions, then they can. And I can also answer questions about Trish's part of the course. So it doesn't have to just be on these lectures. I should theoretically at least be able to answer the questions from Trish's part of the course as well. So you can come and ask about that too. The format of the test similar to last year's. Okay, so what we're going to do, and I've said this to a few other people, we're going to have basically the first part, which is generally short answer questions. So some will just be like 1 mark, what's the answer to this? Like, what is the inner core made of? Something like that. There are going to be some slightly longer ones, which maybe define, so like, what is pore fluid pressure, for instance? That could be a question which would probably be worth 3 marks or 4 marks, okay? And you have to answer all of those. And then at the end, we're going to have 3 longer questions, so probably for 15 marks. And there'll be 2 on Trish's part and 1 on my part, because that's about the ratio of what we've taught. And you'll just have to choose one of those, okay? So you don't have to answer all of them, you'll just choose the one that you feel best able to answer. And the reason that we're doing that is because the exam has some of these longer answer questions, and we want to give you a chance to practice doing them, because we know it's not something that you do with a lot of your other courses. So I think we decided in the end we were going to do it for 15 minutes. So that'll be just less than a third of the test. And the reason for that is in the exam it'll probably be 20 minutes, but we'll ask slightly shorter questions. But if we put too much time and marks into that, then it means we can't cover as broad a set in the first part. And we want you to use this test to identify areas where you're like, I have no memory of that, I need to go back and look at my notes for that section.